First of all, I apologize for my voice today. In advance, I got COVID like 3 days ago, and I'm still recovering, so I might be coughing all the time during the class. But the good thing is, like, our classes are online, and hopefully we would be able to continue the class with no problem. So let's see how much my brain would allow me to cover today. I hope that we can cover as much as I have time. So let's have a quick recap before we continue our discussion about the DES. So last week we spent quite some time to talk about, we analyzed the security of the Vernon one-time path, and then we showed that no matter what kind of adversary we are dealing with, for the case of Vernon one-time path, this algorithm achieves unconditionally security, right? The reason for that was that we discussed that, for any sort of adversary that, can, guess the correct M, having this, seeing the ciphertext and spending a lot of time for computation does not help this adversary anyway. And the best thing he can use to guess the corresponding message is the distribution of the message itself. So that was our way to prove. And then we expand a little bit. We discussed that, the computational version, so we said that it is not the best case, so that we, for one-time path, since that it has very good security, what if we just start to use it? So as we discussed, the only problem is that we have to transfer, in order to encrypt the message, we have to transfer a key which is the same size of the message space as message itself, which doesn't really make sense. For 1 megabyte of message, we have to transfer 1 megabyte of key. So that is like, it would grow proportionally to the size of the key. So one way to pass through that was to use pseudo-random number generator, so that both Alice and Bob share a few bits of message, and then we use this pseudo-random bit generator to expand it to more bits. So therefore, with this idea, ideally we would be able to start with a short amount of seed, which is our secret key, and then we would be able to expand it for quite a long time. And that would be one way to convert the one-time path into a more efficient or practical way. However, once we've seen with the discussion that the moment that we would replace that key with the pseudo-random number generator, we would suddenly turn down the algorithm from unconditionally secure into computationally secure. Then the reason for that, one way to see it is that we cut the key space significantly. And then we observe what are the block ciphers in abstract, and we show that they are basically just a permutation. So based on different keys, you map different messages to different ciphertexts, and vice versa. And then we saw that when we want to have n number of bits for the message space, then the size of the key would grow like very significantly. So we've seen this one, for example, for AES, that if we want to have an AES algorithm to cover the entire set of keys, that would be some terabyte. We need terabytes of bit to represent the key, and it is impractical. And then we discussed that we would move to a practical version, where in the practical version, instead of having the entire space of key, we would have a subset of them. And then obviously there is a difference between these two. So we show that when we are using ideal block ciphers, we can show them that they can achieve perfect secrecy. That means that they're unconditionally secure, no matter how much computational power that adversary has got. But since for the practical version, we have basically reduced the key space. We shrink it into a very small space. Imagine from terabyte of bits, we just shrink it down to 128 bits. So that is a significant, trading. But in return, we turn it into a practical version. But it is obviously for you to see that whatever block cipher that you see out there, none of them can achieve unconditional security. And the reason is because we cut the key space. So last week we landed here. We just started to discuss about the DES. We won't really spend much time on the DES. Hopefully we would get rid of DES very soon, because we are not using and recommending to use DES. It is broken, but it is a warm-up for every course. So understanding the structure of the DES would help you to understand a lot of other block ciphers if you want to study in future. So it was so the DES was become a part of a standard in 1977. The algorithm itself takes a key of 56 bits, and then the message space and the ciphertext space are both 64 bits. So which means that it would take a 64-bit message and 56-bit of key, and then would encrypt it into a ciphertext. So the DES algorithm is what we call it is iterated encryption. Iterated encryption algorithm, just like DES or AES, are a sort of algorithms that if you look at their construction, you see a for loop that there are many rounds, and then the cipher, the plaintext will go in from the top round, and then we would have some iteration with some many rounds, and every round we try to flip the bits in the plaintext and do some sort of linear and non-linear operations, and at the end after many rounds we would be able to output the ciphertext. So that being said, in the construction of the DES, we would have 16 different rounds. And so we start with the key that is only 56-bit. So the first thing, the task that we have is to generate 16 different keys, which is every of these keys are going to be used in one round. And then unfortunately, we just have 56-bit as input to the DES algorithm. So we somehow need to expand this bits to more bits, so that we can generate different keys for every round. So we said that in the beginning, we have 56 bits. We need to have a sort of polynomial time algorithm so that we can generate 16 different bits. Every round key in DES is 48 bits. So if you multiply them together, this algorithm is going to generate 30 times longer bits than the original 56 bit that we have. So that's a lot of bit to generate. So we will see later how this key generation algorithm works. But before we go through and showing different parts of the DES, I think the best example is to stay here a bit. So let me show you the F function, which is what we call it the heart of DES algorithm. So the story is, as I said, this is the round key that goes in. And so the F function would get this round key as one of the inputs, and also another input is X. So if I say this is X, and this is the key I that goes in. So if you notice, our X is 32 bits, it says. So, and then also our K round key is 48 bits. So obviously we don't want to XOR the operation that we want to perform there is XORing them. However, we are missing some bits. We can fill them with zeros, but that is not what it is expected to do in the DES. So the first operation that we have is something that called expansion permutation box. So this operation would take these 32 bits and expand these bits into 48 bits. Soon you will see how this expansion box works, but imagine that we would just repeat some of the bits from the X itself so that we can construct, expand it to 48 bits. Once we have done that, we can XOR, this 48 bits with another 48 bits that we had here. And so the result would be another 48 bits. So far everything is okay, but the problem is that this function should again output only 32 bits. So we somehow need to shrink this 48 bits back to 32 bits. So we would be using some S boxes, which are basically table lookups. And then you will see how this circuit works very soon. So the idea is to, convert that 48 bits into 32 bits. And then once we have done that, we will do a round of permutation. We permute some of the bits, and then that will be it. That will be the output of the f function. So in short, what you've seen here is that the f function would get the input, expand it to 48 bits, and then XOR it, and then shrink it back to 32 bits. So this is mostly what this function would do.
Sorry.
Yeah.
Just the 48 bits, that's just our number we decided, right? Or why is it 48?
Very good question. You need to ask that question from the designer of the DES. That is what
okay.
Right? So unfortunately, for a lot of block cipher algorithms, you see some operations or some key choices that, a lot of time you can, wander around that why is it has to be 48-bit, right? Why not, for example, 50 bits? It is the way that they design the algorithm, okay? All right, so let's move on to the DES algorithm itself. So I would like to, make these things a little bit more simplified. So I always tend to write them in mathematical equations, so it becomes even a bit easier to understand comparing to the original paper of the DES. But before we get there, let me draw a picture of how the DES is, how DES works. So then I think that would be easier for us to imagine. So in the beginning, we would have a message that comes to our system. We said the message is 64 bits. So in the beginning of the algorithm, we would chop the message into two parts. Every part is 32 bits. So 32 bits and then 32 bits. So let me call this one X. Let me call this one Y, right? So the way that the DES algorithm works is that the X comes in, and then this, if this is our f function, let me just draw it first, and then we explain it. Okay, so in the very beginning, what happens is that the f function comes in, and then we first chop the message into two parts. Every part is 32 bits. So we take the Y, this part, this other part, the least significant bits, and then we feed it to our f function along with our key 1, the round key 1. And then the f function, as we said in the previous page, it would do its computation and it would output a 32-bit. We take this 32-bit, we use it to encrypt the most significant part of the message. And then after we XOR it, then you will see that we have another operation which would swap the bits. So now we would go here, we have another f function that now takes this part, and what it tried to do is K2, and right. So as you could see, every time we would use one part of the message, and then we feed it to the f function to encrypt the other part. And then once we have done that, we would swap them so that now we use the result that we got from the last part, we feed it to the f function to encrypt, the first part of the message that we just left it, like Y part, that we just left it untouched, right? And so on and so forth. This thing would go for 16 rounds, and in every round, you can imagine that we would hide a half of a message, and so on and so forth. So this iteration would continue until round 16, then we would have our ciphertext. So let's see how we can represent this in mathematics to make our job easier to analyze the algorithm. So I would like to define a function called phi I, that I denotes the round I from 1 to 16. And then we said that we would saying that this phi I take two variables x and y, and then it takes x, XOR it with the result of f of ki and y, and then it would just output that. So let's make a connection to what we have on the other side. So this part is phi I, right? So what it says is that it takes the x, and then it takes the y, and then it will compute the f of k, y, and y. So f of k, 1 and y. And then once it compute the f, he would XOR it with x. So this is exactly what we've written here. And then he would just leave the y as it is, right, up to here. And then we also would like to define another function, which is, let me just discuss about the function quickly, and then we will go back and see the construction of phi I. So I would like to define another function mu, which would just take x and y, and it would just swap them. So this mu function is a function that is happening here, because you see that we are swapping the location of the x and y. So I'll just define that one as a mu, and that is just very simple. So let's look at the phi function now and see how that is defined in details. So the phi function, if you could see, is just takes y and the key, which both of them, it takes x and y, which are both 32 bits, and then it would output, another 32-bit and 32-bit variable. And it is by the design of this phi that this phi is basically what we call it is reversible. So let's see how is it so. I'm gonna use a property of what we have in the math, that if you guys remember f of FOG in mathematics, that is going to be f of j of x, right? Recall this property that we have in mathematics. We said f of g. So we compute g on x, and then we compute the f on the top of that. So I'm going to use that property over here and show that a phi function is basically reversible. So the idea is that if I compute this phi I twice on itself, so which is phi I of phi I on input x and y, let's see what do we get. So I'm going to keep the first phi I, and then I'm going to expand the second one, so that according to the construction of the phi, the result of applying the first phi I to x and y, we would get this one, x XOR with f of ki and y, and then y. That will be the output, right? So now we need to apply another phi I over on the top of this. So if I apply another phi I, I'll get the first part as in the construction of phi, but we define is that we would apply the fki of y on the first variable, and we just leave the second variable as it is. So if I apply this phi I function again on this, now my x look like this thing, and this is my y. So if I apply that on the entire thing, I get x XOR, this is going to be my new variable, ki and y. And then according to the construction, I have to apply that XOR this one again with f of ki and y, right? And then the second part, it says that just leave it as it is, right? Based on the definition of this phi of I. So now if you see, the result of this would become, when you XOR two same variable, they just get cancel each other. So I get x and y, right? So you see that if I apply phi I twice, then f of I of fi then it would reverse the operation. So This means that by construction, our phi function is reversible. And remember that it has nothing to do with the construction of f function. We can substitute any sort of f function at the end, no matter what output the f function gives, because it would cancel itself. So based on our definition, this phi I will be always inversible. So you may wonder, why is it important to have it inversible? Because the reason for that is because we want to have encryption and decryption algorithm. So when we encrypt the message, we want to be able to decrypt it as well. So we want to make sure that any operation that we define, it is also inversible, so that we would be able to, do the decryption as well. So now that we've shown that, or according to the construction, the first step is inversible. So the mu function now, that the mu function just does a very simple work, and it just like swap the variables. And of course, this is also inversible, and there is no problem with that. So it means that the building blocks of this DES algorithm are inversible. Okay. Now that we are given that, the next thing we want to do is to show whether, after we encrypt and once we pass the ciphertext to the decryption algorithm, can we recover the message itself? So the answer to that is yes. So, so let's check the completeness first. So, of the algorithm. So if I encrypt, when I'm encrypting, I start to encrypt, the first part of the message with the key K1, and then I go ahead and encrypt it with the key 2, and then round 2, and all the way to key 16, and then I'm encrypting this message M. The decryption algorithm in the DES, we would see the construction of the DES. The decryption is exactly the same as encryption, but we would feed the keys in a reverse order. So that means that the decryption algorithm, the DES, we would be the same, but we would apply from the latest key to the smallest key, key 15, key, and so on and so forth, all the way to key 1, right? And to show that the algorithm was correct, for any message from message space, we should have this property, so that we should be able to show that no matter what message you choose, if you do encryption and then you decrypt it, that message with the same keys, and of course with reversing the keys, then we should get back our message. So this is how our encryption algorithm is defined. We have two more small pieces into our algorithm, and that is like the permutation of the message. In the beginning and in the end of encryption, we have two permutation. These permutations are actually not really important, because they are fixed, and they do not depend on key, and therefore really they don't really add any security to the algorithm. It is there by their design. So we would just follow with the definition of the algorithm, and we suppose that we would have them. The way that the algorithm works for the encryption, you start with the first permutation, and then you compute the phi 1 with the key 1 on that, and then you would do swapping, and then you continue with phi 2, and so on and so forth. So if you see this one, phi of 16 of mu of 15, and so on and so forth. So you start with the beginning, which is phi 1, and then you pass it to the phi 2, and so on and so forth. So this is the best way to write it down. And the decryption, we said that is exactly the same, but with the reverse key. So we would start with the key 1 at the end, and then the first thing we would use is key 16. So let's see if the way that the algorithm is designed would actually make sense and make it inversible, which we want to check the correctness. So if I want to write this, expand this one based on these two operations that I have, I would end up with something like this. So I have IP minus 1. I'm going to decrypt first, right? Decryption of encryption of phi 1. And then I have mu. And then of phi 2. All the way to mu of phi 16. So I'm decrypting. And then at the end, we said that I have another permutation. And now if I go back to the encryption, so this is the decryption so far, and I want to write them all of them back to back. So from here, I start to write the encryption. So in the encryption, what I get is this one, IP minus 1, the inverse of IP, and then phi of 16, mu, and then phi of 15, mu, all the way down to phi of 1, and then at the end I have another permutation. So looking into this, writing what I wrote was the decryption of encryption, right? So I wrote that decryption of, what we are discussing here is the decryption of encryption, right? D of E. So you can see that from the middle, these two are inverse of each other, so they're just canceling each other. We show that if I apply phi of I of another phi of I, which is phi of 16, they also would cancel each other. Mu is, we saw that we swap the variables. So if you swap it twice, we get back to what we had, and so on and so forth. So you see that when I apply this one from the middle, they start to cancel the effect of each other. So at the end, what I get is exactly the M that I was looking for, right? So this shows that mathematically, the construction of the DES is correct. And after I apply this permutations and all the operations, the encryption and the correctness of the algorithm is satisfied. All right, but you may wonder how this algorithm is really working now. So I think now that we have enough background of what is going on in these boxes, now we can start to discuss the algorithm itself. So allow me to start once again and go through the details and see how do we do this exactly. So on the input M, which is our message, we said is a 64-bit message. It comes in, we do some initial permutation. The initial permutation, you can imagine that is a fixed permutation table that it says, for example, bit number 1 goes to whatever location, and so on and so forth. After we've done that permutation, we cut this message into two halves. The first half is normally we denote it as X, and the second half we denote it as Y. There are 32 bits. And then the first half would just come here. We don't need to do anything with it. But the second half, with the Y, we would feed it along with the the key of the round 1 into our F function. And then after we compute the F function, we would basically get that result, XOR it with the other half, and then we would apply the mu function, which we would swap them. So you see that on the first part, the first round, we have changed the bits of the left half of the message, but we didn't do anything with the right half. That's why we would swap it so that next round we would change the bits on the right half, and so on and so forth. So the construction algorithm is in such a way that after you do all this computation for 16 round, which means that 8 times you change the bits on the half and 8 times you change the bits on the right half. Then we would feed the result to another final permutation, and then the result would be the corresponding ciphertext. So we have successfully encrypt the message using the key. Okay. So this is for the DES itself. And then another question is that how did we generate those keys? From 56 bits. So the key, it says it is 64-bit because it has some parity bits. So we would get rid of those parity bits, so we would shrink them to 56 bits, right? The reason for having those parity bits is because we want to make sure that, you know, if any of those bits has flipped, we are able to identify, or in the best case, we will be able to correct the corresponding bit that has been flipped incorrectly. But generally, this is the input of our algorithm, which is 56 bits. And then we apply the key permutation. Just like initial permutation for the message part, we also have a key permutation. Again, it is fixed, so it doesn't depend on anything. You just constant, static, you know, there is no randomness on it. So we would flip some of the bits. And then what it does is that, again, just like the original algorithm, we would cut these bits. So after here, we would have 56 bits. So if we cut them into two parts, we would have, every part would be 28 bits. So once we have arrived over here, what we would do is that we would do some rotations, so bitwise rotation. So what it does is that, for example, we, you know, depending on the round number, I think it is not in this picture. So we would rotate, we would shift to the left and then flip that last bit back to the beginning. I think it could call rotational bit, left shift. So, you know, maybe one shift, and then some of the other rounds we do twice. It is a fixed number again, and it is defined very well in the construction of the algorithm. So we would do this rotation, and then whatever it is, and then we would do another round of permutation, and then we would collect this 48 bits as, or only 48 bits out of this 56 bits as our key round for 1. So again, we would continue with this half that we got here. We would shift rotate them again, maybe twice for the round 2. And then once we have done that, we would do some permutation. And then again, from all those 56 bits, there is a fixed table that we would choose 48 bits. And then we would use that one as round 2 key, and so on and so forth. So the rotational shift, if you are wondering what is that, suppose that, I'm not sure if I'm saying that name correctly. The secret is, if somebody knows, please correct me. So if I give you a value called 10100, and I do one rotational left shift, then what would happen is that this 1 is supposed to go back to here. So what I get is that 0, 1, 0, 0, and 1, right? So I never lose any bit, even though I'm using the left shift. But, you know, the most significant bit, depending on how many rotational left shift I do, you know, it would go back to the beginning of this register, and this thing would continue to rotate. Right. So again, how many do we do that? Depending on the rounds, there is always either we do 1 times on both of them, or we just do twice on both of them, and so on and so forth. So once we are done with that, every round we see that we continue this one for 16 rounds again, just like the 16 round that we have here, because every round we are able to generate a round key. Okay. So I'll come back to here. There are some discussions about this key generation algorithm that we will come back to soon. The next thing that I would like to discuss with you is the expansion permutation box. So in the construction, you've seen that at some point, you know, in the beginning of the f function, we need to XOR, you know, our input, which is 32-bit, to a key, round key, which is 48 bits. And I said that we need to expand the input. So this is our expansion function. So what it does is that it would, you know, group the input bits, 32 bits, into the group of 4 bits. So we would have, you know, in total we would have 8 of them. And then since we need to expand this, we need to, copy paste some of the bits from other locations so that we are able to expand it. So every time that we want to expand it, for example, let's look at this intermediate block. So it is borrowing one bit from the previous block and also, borrowing another bit from, the neighborhood block, and also is passing its bit to this neighborhood block so that they all can start to expand 2 bits. And if you continue with all of them, so we have converted them into 48 bits. For example, let's look at over here. So you have 4 bits, the first 4 bits. So this is showing bit number 1, 2, 3, 4. So we have expanded for 2 bits. So we borrow bit number 5 from this guy and we brought it here. And then the first bit is coming from the latest bit, which is bit 32. And then you can see that after we expand them over here in this box, we have in total 48 bits. And it is as easy as it is. So just, borrowing from neighborhood, blocks of 4 bits and then try to expand it to 48 bits. The next one is that if I go back, so I think so far we have discussed what we have over here. So the expansion box. So you see that the input was 32-bit and we just borrow some of the bits and then we were able to expand it to 48 bits. Now we are going to look at this one, S boxes. That the problem is the reverse. We have 48 bits and we want to reverse it into 32 bits, shrink it into 32 bits. So the idea with the substitution box are actually very simple. So we have already 8 pre-computed S boxes. And then I want you guys to look into this S boxes as a lookup table. So we have 16 columns and 4 rows. So again, when we have 48 bits, we want to shrink them back to 32 bits. So we start to group the bits into the groups of 6 bits, 6 bits. So as you can see, the input over here are all 6 bits, 6 bits, right? So the input is 48 bit. And this is how it is going to work out in this table. So we use the first and the last bits. So we have 2 bits, and depending on the value of these 2 bits, we are going to select one of these rows. So with 2 bits, we can generate 4 different values. And depending on the value of bit 1 and 6 together, we are going to select one of these rows. And then the leftovers, the 4 bits in the middle, with 4 bits, we can represent numbers from 0 to 15, right? So depending on the value that they have, we are going to select one of these columns. So suppose they are denoting over here, and this thing is denoting over here, which means that we have a heat in the table, and then whatever value that is written there, which is always 4-bit value, we are going to use that one as our output, okay? So that's how we can shrink, we can imagine that we apply that to every 6 bits, so the result would be always 4 bits. So we would be able to shrink it back to 32 bits. Oh, right. I think I have a very good slide for the key generation. I forgot. So I think you see that in the beginning, as I said, our algorithm, it says that we receive 64 bits. So we said that these bits on these values in these locations are parity bits. So we would just drop them. Oh, the secret that I was talking about was circular shifted leaf. Yeah, I make a mistake there. So with the circular shifted leaf, left, we will see that on the round 1, 2, 9, and 16, we would just do once, and on the other rounds, we would just do twice. And then once we have done that, the compression permutation box that, given that 56 bits that we have generated on this round, using this table, we are going to select 48 of them and from these locations, and that would be our round key. So it might look in the first place that is very bizarre. Why is it so? So most of the time construction of block ciphers, as I said, is hard. There is not much of, a standard approach for, producing or coming up with one of these algorithms. So this is one of the designs that, in 1977 they came up with. So there are some magics over here. For example, if you go back, the value of these S boxes, how do they come from? It's been, very tedious computation. And these values are very important. Nowadays we have them available as a table lookup, but the authors on the first time, they sat down and do this computation to come up with the good values for the tables. These values are not random. You cannot go and change it. If you change it, you would make the DES algorithm to be vulnerable to many different attacks. Unfortunately, we won't be able to go deeper here to discuss how do they come up with these numbers, but there are some mathematical relationship, obviously. They have been, it's a little bit more than that. There are some techniques called differential equation, differential privacy and differential cryptanalysis that they applied, and they try to analyze this table in many different ways to see that the values that they put there are safe. These, as I said, these are different techniques that I don't think we would have the time to go through them. But it's just a piece of advice that when you see these algorithms, don't try to change those values, because those values are they are not random. They have people have done a lot of computation to come up with them. All right. Okay. So this was the discussion for the DES algorithm. So speaking of the security of the DES, so the first thing first is that the key space is very small for, I'm talking about today computation, not 1977. So in 1977, perhaps, having 56 bits and, you wanted to write that for loop to go through that 52 to the power 56, that would take quite a long time. But nowadays, we have, even now, not nowadays, a few years before the AES coming up, people came up with this FPGA board that, they could break any DES algorithm in a few hours. So it was just, there's no magic over here. They don't assume that there is any weakness in the DES algorithm. It's just a brute force algorithm, right? So they try to apply many different keys at the same time. So this exhaustive search is possible through this FPGA. Some people, they came up with this algorithm. They also published the way that you can design this FPGA. So they published the white papers. And well, at that point, everybody could go ahead and, design that circuit and then put them together and try to attack on any DES algorithm. And also, we've observed that there are some weaknesses on the key. So let me go back over here. Any of you think that, what do you think about this key generation algorithm? Do you guys have any opinion? Do you think it is a good key generation algorithm, expansion algorithm? It is a weak one? It is very simple, or it is very sophisticated?
It seems simple, but it's every time it's dependent on the input, right? So if the input is a really, really good key, then maybe it's okay.
Right, I agree with you. So in order to understand this very in a clear text, what if I give as input my key that I choose all 0 bits? Okay, I pass my key all 0 bits, and let's see what happens. So in the beginning, I drop some of them, which is fine. I just get 56 bits, which are all 0. And no matter how many secret left shifted left shifts, what was that secret that I apply, this register would always remain 0, right? No matter how many left shifts that I do and I swap this bit to the end up to the back of this register, I always get 0, right? And then with this box, no matter how I choose this resulting bits, again, I get all 0 bits. So which means that the ground key 1 would be all zeros, key 2 would be all zeros, and so on and so forth, right? And what if I choose just 1, 1. So 1, 0, 0, 0, and 0, right? Again, what happened is that there is only 1, 1 that is passing around, right? So the first time that I cut this one into half, so this part would always remain 0. And then the other part, this bit 1 would be shifted somehow into the thing. So again, as a result, the majority of the bits of the key would remain 0. Correct? And if we go back to that f function, and if we XOR something with all 0 bits, then we don't change it, right? XORing with 0 would the variable would remain the same. So the problem with that is that the key is not really changing anything in our algorithm. Then whatever it is there, because our bits are usually 0, then everything would remain the same. Then this is the reason that I just wanted to discuss in different way that, this is a very good technique. You can start to see this one for any key generation algorithm that you have. You start with these counter examples. We assume that we choose a key in random, sure. But, there is a chance this bit would be chosen. There is a chance that this key is being chosen, right? We can't say that they always have half of the bits 0, half of the bits 1. This is our key space. We already have a very small subset of keys. And then these keys could be chosen. And if they are chosen, then you see that the message wouldn't, the ciphertext of a corresponding message wouldn't really get changed. So this is a serious issue. And then, if you want to, in future, we want to get a better algorithm, we really need to keep an eye on that. All right, it looked like that it is your break time. So what if we have 10 minutes break and we come back soon?